David Colwell founded Trannan Furniture in mid-Wales in 1976 to produce and market his own furniture. His designs use steam-bent components made of solid ash from forest thinnings. He had a long-standing interest in sustainable materials, as well as contemporary design for manufacture. He wanted to combine these interests to build an ethically engaged business which brought out the benefits of craft-based production. To start with, the most important of these benefits was the low capital investment he needed. He took a hands-on approach to manufacturing, which meant he could see the work through from beginning to end. One result of this was that David and the employees he gathered round him were better able to value their work and claim ownership of it. As time went on, it became clear that this also meant that quality control is built into the whole process of design, development, and production. All this might sound romantic and idealistic, but this is far from the reality of Trannan Furniture today. The company moved to Wilton, Wiltshire in the early 1990s. The manufacturing ethic which David developed means that he can compete with comparable mass-produced furniture on quality and price. He is also able to be adventurous and experimental in design, as he is not weighed down by major capital investment or by company hierarchy. At the core of Trannan's success is the material, native ash, and the techniques used to work it. While steam bending comes out of the craft tradition, it is ideally suited to batch production. In this context, it has other benefits, such as low energy use and low material cost. It also allows manufacturing to key into the forest economy, making maximum use of timber as a renewable resource. With the quality of its products and its sustained presence in the furniture market, Trannan Furniture has proved that manufacturing can combine business success with a worldview which provides for customers, producers, and the environment.
This is all wood that we will be bending. It's all here, especially for steam bending. It's all European, with the exception of beech also. So none of it's tropical. With the exception of beech, it's all ring porous hardwood. Now, it's actually a very important distinction. Ring porous hardwoods have the wonderful combination of both growing fast and being strong. That's to say, the faster they grow, the stronger they are. This timber here is all ash, which is really the prime ring porous material, although other ring porous materials would include oak, elm. In fact, many of the common, particularly British timbers, are ring porous. The fascinating thing with the strength of it is that, say, the faster it grows, the stronger it is. And if we look at this piece here, we'll be able to see why that is so. This is a perfect example of a piece of fast-grown ash. That we have these first year, second year, third, fourth, fifth, terrifically fast growth rate, about 5 rings to the inch of thickness. And looking closer on here, you can see that there's these two different sorts of growth here. There's this porous growth, the darker, yellower pieces, and these are made up of tiny little tubes. In fact, they're not that tiny. I can see them quite clearly with my naked eye. These run, these are they're spring growth. It's the first thing the tree does is to grow a ring of these around its outside, around here. And that happens in early spring, the very first thing the tree does. And up through here comes the moisture from the roots up towards the leaves. So it's actually, this is where the tree's food, where it breathes, its life depends on these tiny little tubes. But the tubes have they've got no strength. There's virtually no material in here. This is 80% just cell walls and open structure. It's the piece here, which actually is better seen in the middle of the tree. Here we've got a bigger growth rings still. Between there and there, this 1 year's growth this bit in the middle here contains all the strength of the timber. This is solid matter. This is fibres and lignin. This is the real thing in there. And you can imagine that since these rings through which the tree feeds are fixed in size every year, they're the same size, and they're a product of how much crown the tree's got, the bits between them are variable. So the faster the tree grows, the bigger the ratio between these tubular respiratory ducts and the solid material in the middle. That's why these ring porous hardwoods have this wonderful phenomena of having this, the faster they grow, the stronger they are. Now, if one looks by contrast to this piece, which is a very slow grown piece of material, it's the same stuff, it's ash, and you can hardly see the growth rings here. They're so close, so slow. And this piece of wood will be a fraction of the strength of the fast-grown piece. There are other timbers which can be steam bent. This, as I say, is ash. Oak can be steam bent, and it bends to a very tight radius, but is about twice the price of ash and isn't as strong. Beech is commonly used in steam bending. That's not a ring porous hardwood, in fact, but again, it doesn't have the ultimate strength of ash. Well, it can be bent tighter. Elm bends fantastically into incredibly tight shapes, but again, it has virtually no strength having done so. And yew, which again can be bent and is bent, of course the sections there are very small, and there's a lot of very good reasons for not using yew, not least of which is the fact that it's actually quite toxic. Its dust is quite toxic. So ash, from my point of view, combines strength, relatively low price, and I think it's a very pretty timber as well. We spoke about fast growth rate. In fact, what happens is that the smaller the tree, almost the faster the growth you get. So the ideal material for this steam bending is frequently forest thinnings, which of course have the use of them has a tremendous benefit in the context of forest management. Amongst the advantages of timber, which is a truly remarkable material, it's got a very, very high strength-to-weight ratio. It's also one of our only sustainable structural materials. Then it absorbs atmospheric carbons in its growth, so that from an environmental point of view, the impact of doing this is more or less neutral. We absorb as many carbons as are put out into the atmosphere in the process of manufacture, which is a fairly unique situation. Mechanically, what the stuff is a composite. It's like fiberglass or concrete, in which there are fibers which are of cellulose, and they're stuck together with lignin, which this is actually very significant when it comes to bending the material. We'll need to remember that. What has to happen if we have a straight piece of wood like that, in order for it to be curved, what needs to happen is that the outside must stretch, or the inside must compress, or both. Now, in practice with timber, both is what happens. So you can produce a bend in timber up to a point, and it will behave like that. The top will stretch and the bottom will compress, more or less in equal measure. What happens is when the limitation of that situation is that the bend will break in tension, the top edge will break. And what we do to avoid that is to put the piece of wood, to stop it stretching on the outside, we put it into a strap. The top of this piece here can represent the strap, and as it's bent, all the work happens in compression, like that. This is a strap, and we'll see shortly how this is used in practice. The one disadvantage with using that is that there can be failures in compression, which are nowhere near as severe, but you can see here quite clearly on this piece of wood how the inside face is compressed over much. Now, in fact, we may have to limit the amount of compression that happens in the bending process. But this is nowhere near as serious as a break in tension. We spoke about moisture content as well before. There are three very good reasons for the moisture content being kept high. The first one of them probably is the fact that it's cheaper. That timber unseasoned is much cheaper than seasoned timber, and the steam bending process is half a kiln drying process. So we actually get that bit of what is usually quite a costly exercise for nothing. The second is that it's inherently more flexible. This is a piece of twig that's still green, still got moisture in it. This is a piece of twig which is dry, maybe 10% moisture content. It has no strength. And the third reason is that the timber is a very, very poor conductor of heat. Anyone knows who's struck a match that the first they know of the flame reaching their finger is when the flame actually touches their finger. Were that match metal, were it say a sparkler, that in fact you get a warning of that the heat is transferred through the material and reaches your finger first. That doesn't happen with a match. Wood is a remarkably good insulator, and therefore the higher the moisture content of the timber, the better the transfer of heat through. Now when it comes to the vehicle for the heat, it is incredibly convenient that lignin softens at 100 degrees centigrade. Now what's so really handy about that is the fact that that is the boiling point of water, that is the temperature of steam. And that is why the process uses steam as a means of very readily available, very low-tech way of achieving 100 degrees C whilst not drying out the outside of the timber, retaining the moisture content of the timber and it arriving at exactly 100 degrees centigrade. This is a bending strap. When we looked at this, we discovered that in order to get a tight bend, we needed to stop the outside of the curve stretching. The way we do that effectively is simply by having something over the top here which won't stretch and a block at each end to contain the length of this. So as it bends, all the work is in compression. And that's really, this is what does it. There's a block at the end. This is stainless steel. It can in fact be mild steel, but it needs to have something like some polythene over it to stop it staining the wood. When the wood is hot and has been steamed, it picks up every single little mark from your fingers, so having that clean is a tremendous bonus. The design of the strap has an adjustment on it. This block at one end needs to be cut with an angle, and you need a wedge at the same angle there, so that will give you some adjustment. And I've found the simplest way of doing it to be to bend the piece of steel around a block of wood and then bolt it through so that it's actually contained. This won't move because of the two bends, really. And the bolts through here additionally hold on this piece. Now, the significance of this piece is that it stops this from bending backwards. Were it not for this, as the compression was exerted along this strap, this would simply bend backwards to release it. This stops that from happening. It has the additional benefit that if this can be extended to make it longer this way, or indeed longer this way, in order to use it as a handle. You can get greater leverage by modifying this one way or another, so that each strap has to be designed to a point to suit the need that it's going to be applied to. The strap that we'll be using is in fact this one. Mainly. Now this has been, again, it has the same piece of stainless steel. It has its back board here, but because of the length of these pieces, as these compress, they're going to want to go outwards as well. They're going to try and lose this compression any way they can. And so here, we've contained the sides by putting these cheeks on the side of the strap here. That's just it's an additional modification. The other thing that happens in this particular bend is that these straight lengths have this backing board extended all the way along the back for all the straight section. Not only does it keep the timber straight in that section, it also means that you've got a built-in lever. This is a mould. In fact, this is the mould that we make this component with. Now, what you'll notice from that is that the mould, in fact, is a tighter bend than the final one will be. And in fact, the final chair is out here somewhere. So when you make the bend, you'll see later it'll be bent around this form. This is actually a tighter curve than the one we finally want. I usually make the moulds about 10% tighter. Now, in fact, what happens is that the shallower the bend, the more it needs to be overbent. The tighter the curve, like this one, doesn't have to be overbent all that much. The other thing that you can see from this is it's an extremely crude object. This particular mould has made several thousand chair frames, several thousand of these bends. I don't know quite how many, but you can see it's an extremely simple thing. But what is necessary about it is you have to work out where you're going to put cramps and to accommodate them to start with. We've also put a backing board on this one in order that the bend and the strap, which in fact is the strap we were just looking at, this large strap is the one which will be going round here, to make sure that you have adequate means of holding it to keep the whole operation as simple as possible. When overbending, there's no real problem. If you've bent it a tiny bit too tight, or indeed if it's not quite tight enough, some adjustment can be made, particularly if it's making the bend wider, can be made in the curing process. When we look at that, you'll see that we can easily adjust the shape, relax it a little bit when it's been bent, and cure it at a slightly wider angle. These are the steam boxes. This one, they're actually both the same volume. This one is the one not in use at the moment. So they're the same volume but the different length. This is for long components. What we have here is a stainless steel liner. Then we have insulation around the outside of it, and a door, which in fact in this case is rubber-faced, which closes up and seals it. There's a rack in here, which is for putting the timber into. This one here is in use, and the timber in here. You need an hour to the inch of thickness for material. So from the box being hot, these pieces here, which are 12 millimeters, they need half an hour. These pieces, which are 25 millimeters, need about an hour. It doesn't actually matter if it goes more than that, within reason. And you can see here there's a generous supply of really hot steam coming out. And just lock that back up. You can hear the hiss of the steam coming out through the vent here, at this end here. And now we maybe just go and have a look at the steam production end. Here we have the water reservoir. Water is fed from here just by gravity into this chamber here, which in fact is a cattle feeder trough. And inside it, it has a small reservoir of water whose level is kept constant by this float valve here. The constant level there is in fact reflected in this boiler because it's directly fed through this tube. So this only contains about maybe 1.5 pints of water, and it's heated then by this pretty fierce gas flame, out of the top of which comes the steam here. That is then fed via a valve on the bottom here, either to the top box or to the bottom box. Right, now let's do some bending. The first essential is you need a good pair of gloves, because this stuff is going to be very hot. Let's pop those on. Now what needs to happen here is that these, we're going to bend 2 of these at once, these need to come out and they need to look dry. If they're not dry, they've got moisture on them, that's because they're not hot enough. We need to be quick with this. Now this is Wayne who's going to give them a hand. We just check for that their natural curvature is the way we want it to be. And we screw up these end blocks, clamp the 2 pieces in. in with the key, and we just turn it round. And there we have two chair backs. They're compound curved in both directions. You see the speed of production on that. And not only have we got these two chair backs, we've also seasoned the timber at the same time. So we've gone from this very agricultural process, agricultural material, in virtually no time at all, to a seasoned, virtually finally finished component for a chair. Right, let's do some more. Okay. Another pair. Perfect. This in many ways is the simplest kind of bend. It's within its elastic limit of the material. It isn't stretching the material more than it can stand. And it's simply bent over this former and held in place like that. And it's allowed to cool and for the air to get around it, and it seasons in that form. This is a bend exactly similar that has already been seasoned. Now, the reason that it can be bent as easily as that is because the width of the material here is the relationship between that and the radius of the bend is sufficiently great that there's no need to put a strap on it. The material will stretch some and it will compress readily. The bend is actually made easier still by virtue of the fact that this end here, because it tapers, that it's inclined to want to bend in the thinnest section. So this gets the bend nice and near this end. When it comes to making the chair out of it, in fact, it also means that this end can be set into a tenon and this end is thick enough to be a leg on the floor and have sufficient mechanical strength. So here the shape of the wood is completely in harmony with what is required for the steam bending process. We're going to move on now to a simple strapped bend, but symmetrical. Sean here's going to help us do this just to get this level at the far end. Right, the strap here is long enough to act as its own lever. So round it goes. It's clamped in the middle. And then it's bent symmetrically around this shape. Round it goes. Round it goes. You put a clamp across it here. Just to hold it into shape. Then Sean puts a clamp across this end. In this case, the bends are done in pairs, partially because it doubles the speed of production, partially because any irregularity in the timber is evened out, that you're unlikely to get two pieces of timber with a blemish in the same place, and the timber will always bend where it's weakest. So this way, in fact, one piece supports the other. The strength of one supports the other. The whole sequence of production on this is that there's enough time, in fact, to do this activity every 20 minutes we can do 6 of these strapfuls. That gives us 12 bends every 20 minutes. They can then be cycled, so that's 36 bends an hour, in theory, from using this method just for the two of us. The bend can be removed from the mould pretty quickly. You want to take that off there, Sean? The amount of time on the mould is not very important. The time in the strap, the 20 minutes is the minimum. Now the other thing that can just be seen here, you lift the other end up. pop this on the floor down here. What can be seen here is the tendency for the bend to belly out here, and this we overcome by tapping in this wedge, and then we can just tighten the cramp up round it. Now when we do the next bend, which will be an asymmetrical bend, you'll see how we actually make use of that to get a reflex curve. The other thing that's noteworthy about this process is the chair this is for, the stacking chair, actually uses the fact this is overbent. So in production, the bend is sprung out and it just flips back onto the two dowels that run through it here, so it doesn't need cramping in final production. So the bend here is much tighter than it needs to be, but this greatly eases the assembly situation. There, that's done. We'll come back to that in 20 minutes, half an hour's time, and take it out. With these bits of wood, we'll make an asymmetrical bend with a strap. Straight ends. Straight ends. Okay. Yeah, working a bit harder than last time. Okay, right. Now what we're trying to do here is to get a bit more value for this re-entrant curve into this bit of the mould. So we're going to build up the compression. As we pull this round, we'll be building up the compression on the inside of the curve, and hopefully it's going to flip in to this re-entrant shape here. Okay, let's go. There, you can see the shape there. The metal, good. I think we're actually do is whack that down a bit. Yeah. In fact, the whole bend has moved round. We can adjust it on the mould. As long as it's square, there we are. That's good. Just a question now of getting the mould off away from the bend. The requirement to keep this re-entrant shape here means that it grips, of course, onto the mould. But there you can see it. In fact, we've got a straight piece on this section, and this bit's curved, and this curve here we've just got for nothing, really. It's a question of having bent the thing around and built up the compression, round and round and round here. And here, it needed somewhere to go, and it's sprung back out. So all we've done is helped it and made a mould to fit it. That will need to be in there for at least half an hour before we release that from its strap, though. We're going to do some powered bends now. Select the best end of these for putting the bend in, and pop a wedge in, just as with the other strap bends, to keep the timber in compression, stop it breaking in tension, into the press, like that. This tie bar's lifted up. And the only real benefit of this, over the hand bends, is that one person can do it. There we are, 2 bends. Again, very, very fast, very accurate. Well, we have here all the pieces we've been bending today. We started off with these bends, which are unsupported, just simply bent across across a camber. These bends here, again, they're unsupported. And then we have the strapped bends here and here. Now, okay, we've got them bent. Now, what's actually happened whilst we've been bending them is that apart from the steam heating up the lignum and allowing the fibres to move across each other, as described initially. The other thing that's happened is we've brought the whole of the moisture content of this timber, the 25% moisture content in all this timber, up to boiling point. And what's happened is it's actually allowed it to start rupturing through the cell walls. It's actually started moving out of the timber. Although it came out covered in steam and moisture, the inside has actually probably got very slightly drier, but certainly the moisture's become much freer. And what this now allows us to do is to dry the stuff down. The way that we do it is in this dehumidifying kiln, which is a high temperature kiln. It can be done simply by air drying it. Best of all, it's probably done by putting it in a hot place, a boiler room, something like that, which is going to be maybe, the recipe is 100 degrees Fahrenheit if you can find it, but it'll only take 9 hours to go down to, say, something like 12%. The longer the better, obviously, but this will simply dry in an ambient humidity, say in a kitchen or a living room or something like that. It'll take rather longer, clearly. When they're dry, then they're set. So in our kiln here, we set them more or less overnight. And it could be that if you had a very hot, say, boiler room, for instance, with air circulating around it, you could probably, again, do it in more or less that sort of time. Now, in order to dry them, these free bends, the bends which don't have a strap, the unsupported bends, are simply left in the jigs that they've been bent in. And the initial design of the jig for bending them needs to take into account the circulation of air around them. So none of these are a problem. When it comes to these strapped bends, what we do is actually release the bend from the strap. So in this particular case, let's take these bends, which we did underneath the pneumatic ram. These bends end up going into a jig a bit like this. Now in this particular case, there are the bends. They've been removed from their straps and they sit into this specially made jig here. It then has this little wedge that sits there and it goes. All that matters really is it holds it in its shape and allows the air to get round it. Now what I'll do in fact is to show you another common way of doing it, which would be, say, for these bends, and these ones are held. In fact, the system for these ones is the same using this. It's the same as these, same as any bend which comes right back on itself. It's actually extremely simple to do. Just knock out the wedge, push that down, and then tap out this wedge here. And those bends are gradually moving out. Gradually moving out. That's because the outside here is still wet from the steam. The inside's pretty dry. And all we do is to have, again, we dry them in pairs. And I usually just pull this up so that it's somewhere like that. And there. Those two can now be cured in that form. They'll be seasoned in that form. And say the fact that they've been steamed, that it's gone a long, long way towards reducing the overall moisture content and making the moisture that's in the timber freer, so it will come out much more easily. This is the chair that we saw being bent. These are the long bends we saw here, and which were done with the long strap. These ones here are the free curves that we saw being done without the strap, unsupported bends. The design limitations of the process are that we aren't really capable of determining exactly how thick this is because of the shrinkage of the timber. So we're talking about plus or minus maybe 1/4 millimeter in this thickness. So all the joints that we make into this plane have to take into account the fact that we don't know exactly how wide that is. We do have slightly more control over the width of this. This can be sanded afterwards to be fairly accurate, so that these holes, for instance, can be in the center. But this also provides a very convenient joint in that it doesn't really matter, plus or minus 1/4 millimeter or so, how far this sticks out through the end here. You also notice that when we bent these shapes, that they were pointing inwards, they were overbent. And we've used that phenomena so that when the chair's assembled, the legs are sprung apart and then they spring back into this joint here, which means that there's no tendency for the chair to want to spring out. But the fact that we have this rail through here, holding these two bits in, again is in sympathy with the bending process, because it would be very difficult to absolutely guarantee the width that these legs would come to. It wouldn't be practical to do it without having something here to restrain and control the width of the bend at this point. With these members here, these have to be finished planed all round before they're bent. So we have this tapered section put on before they're bent, and the width has to be put on here before they're bent, and we have to live with the dimension that this ends up being. In this case, and the reason that we have to do these edges here at the same time is because, in fact, with this bend, there's a slight camber. The thing twists. So that is not a straight line, a flat surface. If it hadn't got the camber, if the legs didn't do that, we would be able to thickness those after the bend had occurred. But we get round that, in fact, by having a tolerance here. We have several different sizes of this little component. So the legs are put into a joint in here, pushed apart, which crimps them into these corners. Then this wedge goes in, and apart from serving a visual function, it also serves two mechanical functions. One is that it keeps these legs apart and crimped into here, so again it means the joint is pretty strong even without any glue. Then it takes up the tolerance, the difference in width, through the batch of these different leg components because of the shrinkage rate. With this chair, we have the back, has the back on it here, which we saw being bent with the twist, with the mold with the twist in it, and these components here are the ones which were being bent underneath the pneumatic ram. As we said with this chair here, the section isn't consistent, but in this chair, because the amount of bend in this component isn't very much, and it's flat in that plane, we can actually plane this down after it's been bent and seasoned very accurately. We can make this absolutely spot on in width. So that the joint here is just a conventional mortise and tenon. The width of the material here, which isn't consistent, is disguised by the fact that it has this little chamfer on the top, on each side of the shoulder of the joint. So that allows this to be inaccurate, but this, in fact, can be absolutely spot on. Similarly, that if the bend isn't, again, absolutely spot on here, then we can take that up with the method of attaching the seat, which is laced on, and that has an adjustment here through these little buckles. Where the back's concerned, you saw how quick it was to produce them. Now, in fact, what the three-dimensional shape of the back, which is the important bit, this bit here for comfort, the curve in two planes, as we saw, that's made possible by looking very closely at the profile shape here. Were this not wasted away at this part of the shape, there, if that were a bit fatter, then in fact it would split across there, but it's because this shape has been tailored very precisely to what the wood will take in the way of a three-dimensional curve, that we can get away with it. So we're working here very, very closely indeed with what the wood wants to do. The wood is, in a sense, having more say in how it's going to be than I am imposing on it as its designer.